So again, routing protocol scalability. My name is Alvaro Retana, and I borrowed all the slides from Scott, Jerry, and Daniel, who work with me over at Cisco. What we're going to talk about today is the building blocks of a scalable network. We're going to talk about hierarchy. We're going to talk about redundancy, about addressing, summarization, and how those things relate to routing protocols. Specifically, we're going to talk about ISIS, OSPF, and BGP, which are the protocols that I'm sure we care about here today. I am assuming, of course, that all of you already know routing, so I'm going to try not to go through any of the basics or any of the things that we already should know of any of the protocols, but I will go into the parts of the protocols that are related to, again, hierarchy, redundancy, and addressing and summarization of the protocols, and how to use them, to use these building blocks with the different protocols to build scalable networks. So of course, as I've been saying, the blocks are hierarchy, redundancy, and summarization. So the three things that we should always strive to keep in mind when deploying a network, when building a network either from scratch or we're trying to grow our network to make it stable. There is a very tight relationship between the three of them and with three other important goals that are usually present when we design a network. And those are generally convergence, stability, and scalability. Most of these, or some of these goals that we want to keep in mind when designing a network sometimes conflict with each other. They conflict because to achieve faster convergence, we're talking about taking aggressive approaches to changes. Maybe tweaking our timers to be lower to have faster response. But that can lead, of course, to instability, which goes head-to-head with one of our other goals, stability, of course. And all of this, as the network becomes bigger and bigger, it becomes more and more of a necessity to find a compromise between the two, which is exactly what we're going to try and talk about today. So hierarchy. This first part, of course, just to lay down the groundwork as to what all of this is, and then we're going to go into the actual routing protocols. So hierarchy, of course, we're going to say it is going to refer to the fact that we can break the network into pieces by function. So we can isolate the functionality, the characteristics by different parts of the network. Usually, we're talking about things like a backbone, a core, an access layer, a distribution layer. These are important because then we can assign functions to each one of these, and the characteristics that we're going to need to build a network to design the protocols are going to be in accordance with these functions. Usually, and this is, of course, a clear example, usually things like in a distribution, like a core distribution and access layers, we have in the core layer, we do forwarding of packets. We want to make sure that there is connectivity for the whole network at the core. In the distribution layer, we offer services like route summarization, traffic aggregation, etc. And of course, in the access where we do all the packet filtering, all the packet classification, and where, in this case, customer entrance into the network. This distribution of functions is going to facilitate the scalability of the network. We're going to let us identify where we need to grow our network and how and why and etc. And it's also going to help us with the stability of the network by isolating parts of it. So this, of course, makes clear reference to what we're going to talk about later, we're going to mention later, which is areas. Use of areas in ISIS and OSPF, for example, where we're specifically isolating in parts of the network the functions. The hierarchy is not mapped directly throughout all the layers of our network. When I say layers in this case, I mean like the OSI layers. They're not mapped directly. Sometimes we have a clear core where we do our connectivity, where we have our fast packet switching, where we have fast links, big pipes, etc., and we go down all the way to the axis where maybe the axis links are maybe a little bit slower. That doesn't necessarily map directly to the fact that we need to have areas or not in our IGP. Or it doesn't necessarily map to the fact that we need to have a hierarchy of reflectors, for example, in the case of BGP. So we may still have a network that has only one ISIS level, for example, and still has very clearly identifiable hierarchy. Still has an access layer, a distribution layer, and a core layer. So the important idea about this is that we want to be able to identify the different functions and be able to then isolate, in some case, the functions and eventually correlate this to routing protocols. Redundancy, of course, means having an alternate path, a backup, means having additional resources in the network in case of a failure, or not only in case of failure, but to use in the normal course of the network. To have different paths of connectivity between endpoints. Redundancy is good because it lets us have increased bandwidth, lets us handle more traffic, lets us have more stability, because if one of the paths fails, we still have the other path. So it helps in the stability of our network. However, we all know that too much redundancy can be bad in some cases. In cases where we need, of course, more adjacencies to be maintained, the trees for IGPs are going to be bigger and more complex. The route information must be propagated through all of these extra links, and especially in the cases where we have parallel links, or multiple massive parallel links between routers, we get into extra redundant flooding of information across the network, which of course results in more processing for both the sending and the receiving nodes. So redundancy is a good thing because, again, it helps in our stability, but it may be not too good if we overdo it. The key, of course, is to find the balance between the two, to find where it's good enough, but where we're not affecting the actual performance of the protocol or the network itself. And addressing summarization, which is the third block, it's very straightforward. We only need to design our networks, address our networks with summarization in mind, so that we can eventually carry more routes, because we can aggregate and summarize the information. So in places like the core and the hierarchy, going back to the hierarchy, in the places like the core where we're going to have connectivity information for the whole network, then we can carry more information because we have aggregated routes. This may help in our conversions, because if we have less information to process, so changes may be faster. It, of course, increases the stability, because if you have an aggregate in your network and a component of that aggregate changes, the aggregate is usually not affected. So you can then isolate changes in parts of your network to only those parts of the network. Of course, you also always, as with everything, you have the flip side, which is improper or excessive summarization, or maybe not even improper, just some summarization may lead to loss of information and things like non-optimal routing. If you don't have specific paths, or you don't have specific knowledge, that coupled with redundancy, for example, where you have more than one path to a specific destination, you might be faced with non-optimal routing. Of course, each of the protocols has its own way and its own places where you can summarize, and you can either limit or add actually information. So during all this talk that I'm doing this afternoon, most of it I've tried to keep it as generic as possible. As you can see from the slides, and of course from the first slide, I do work for Cisco. So some of the examples and configurations that you can see are, of course, Cisco. But all of them should apply to any vendor. So the objective of this today is to talk about some of the characteristics of how protocols scale or can scale. Again, relating them back to redundancy, hierarchy, and summarization. And yes, I have, as I said, specific examples with Cisco configurations or with Cisco timers, defaults, whatever. But they should all apply, and I'm sure any of the other vendors can probably do exactly the same thing we do. Having said that, also feel free to ask any questions at any time or make any comments if you want to. We basically have two parts to this afternoon. The first part is we're going to talk about link state scalability. What I chose to do was talk about link state, not first ISIs and then OSPF. The reason is the issues and some of the solutions are very similar. So this is not intended to be an ISIs versus OSPF type thing, but it's just easier to talk about what the issues are, what the solutions are, and how each of the two protocols address them. And then we're going to talk about BGP. So some of the issues with scalability have to do directly with the flooding of the LSPs or the LSAs, how they get propagated throughout the network. There are many things that influence this: the number of neighbors, redundant paths, the type, size of routers, memory in them, the scope where these needs to be propagated, which is reflected, of course, in the size of the network and the number of links. So it goes back to redundancy. And the other part that is very important is how fast can I detect that there's a change, so that now I can send my new LSP or LSA information across the network. And the other part is, well, okay, now that I actually received the information, well, now that I actually know that something changed, well, I need to do something about it. And that something is basically run SPF on the new information of the network and find the new route or the new path to that. So we're going to start with some hierarchy. So we already talked about some of the benefits of hierarchy. Specifically, we can hide some of the instability that may happen in some parts of our networks from the other parts of the networks. What that helps is in then only having to act on the changes in the parts of the network where the changes happen. So that's, of course, the concept of areas in ISS and OSPF. We can isolate the changes for the most part. We only have to run the computationally intensive part of the calculation, which is vector algorithm, where the changes happen. Yes, in other parts of the networks, we might have to run a partial route calculation or a partial SPF, but the more computationally intensive part of the algorithm, which is the actual that vector algorithm, has to be run only where the changes occur. So by isolating a routing to the areas, to an area or to a part of the network, what we're doing is we're reducing the size of the tree that we have to calculate, which should result in saved CPU, some saved memory maybe. There is some impact, as I said, but the impact is hopefully a lot less in the other areas. So in a case like this, where we have this is a picture of an ISIS network, we have maybe a route flapping in one of our level 1 areas. This information is, of course, propagated across the area. The nodes in that area need to recalculate the SPF, need to find what the tree is, what the new tree is. In this case, a level 1, level 2 router will flood information about the reachability or not of this network throughout the layer 2 backbone, because, of course, the level 1 information is sent over to the level 2 backbone. Everyone in the level 2 backbone will have to act on this, but will not have to calculate the whole SPF, run over all the information. But in this case, all it's going to do is run a partial route calculation over the changes. So yes, there's some impact. The impact is a lot less. And as the information gets propagated across the level 2 backbone into another area, in this case off to that level 1 router over there in the end, it doesn't have to do anything. I mentioned in there route leaking, which is something we're going to mention a little bit later. So address summarization, we already mentioned, is a way to reduce the number of prefixes that we have floating around in our network. It's a way to aggregate that information so that changes in some components don't affect the area itself. And then we can, of course, increase the stability of the network. There are different ways and places where you can do summarization in both of the different protocols. In OSPF, for example, you can do summarization in area border routers or at ASBRs. Or in some cases, when you use NSSA, when you're translating Type 7 Type 5s. There's basically three places where you can do summarization. In ISIS, you can do summarization both when you're bringing routes from the level 1 into level 2, and if you use route leaking, when you're leaking from level 2 into level 1. You can summarize there. Or if you're redistributing external information into your ISIS cloud, anywhere, basically. So just the way you summarize in OSPF. If you're doing it at the ABR, what you want to include is a range, which is the aggregate that is going to be advertised for a specific area. And if you're summarizing at the ASBR, these are routes that are external to the protocol, so we use the other command, the summary address command. So again, what this is going to do, reduce the size of the database, reduce the size of the routing table. Optimal routing, I've mentioned this a couple of times, which may be the result of maybe too much summarization, maybe the result of the types of areas that we use, or like the default behavior in ISIS, where all level 1 only areas are stubs. So they don't get information from anywhere outside. So suboptimal routing happens when you don't have end-to-end information about a specific destination. When you're sending packets to someone across your network, and the source or one of the transit routers for that information doesn't have complete reachability information for them. So this is a specific case, again, where you have in ISIS, for example, if you're not using route leaking, where all your level 1 areas just don't get any information from other areas. So you have to rely on your closest level 2 router to get out. If you have more than one exit, then this can result in suboptimal routing. With OSPF, the behavior is a little different in that by default, areas receive all the information from the other areas. It's only in the cases where you configure a special type, a stub type of area, either a stub or a totally stubby or an SSA area, that you may end up with not having all the information. Of course, the different type of areas allow you to learn different types of information. So the amount to which you will have or not suboptimal routing is going to depend on the type of area that you have for OSPF. This is just a quick example. And all we're doing in this case is we have 3 areas, and we're summarizing. And in this case, we're sending a packet from this APR down there to a destination up here, 10.10.20.1, but because of the metrics and the summaries that we're receiving, we get suboptimal routing. Just a quick illustration of what can happen. Of course, in this case, we are summarizing at both APRs. So usually, suboptimal routing happens when you have more than one way out or way into your area. If there's only one way to get there, well, there's only one path you can choose, right? There's no way you can choose the wrong one. So it only happens when you have, again, the combination of redundancy and summarization. Of course, coupled with, in this case, a hierarchy, where you have your backbone and your areas connected to that. So the important point here is that while hierarchy, redundancy, and summarization are good things for your network, are things that are going to let your network grow, there may be the cause of things like suboptimal routing that may not be the results that you require in your network. So as you know, as with everything, you need to not only understand how the protocols work, but understand how they're going to work in your specific network when you're configuring them and deploying them. In both ISS and OSPF, we basically have a two-layer hierarchy. In both of them, there is a contiguous backbone, and areas are attached to it. The difference between them is in ISS you have a level 2 backbone, and then areas are connected to it. A node can be part of only one area. So that's probably one of the big differences between the two protocols, in that basically the border between areas is not in the router, but on the link. So a router can have, of course, neighbors in different areas if it's on the backbone. And if you're running OSPF, you also have a backbone with areas hanging off of it. The backbone is, of course, called Area 0, always. And a router, as opposed to ISS, in this case, you can have a router be part of multiple areas. The same algorithms that we run in the backbone, we have to run in the other areas. So the SPF is the same algorithm. Remember that all we're doing with areas is cutting the scope of where we have to run, and reducing, hopefully, the information and the amount of information that we have to calculate over it. It is clear that in the backbone is where we're going to have the most information flowing. So we'll have to run PRCs or partial SPFs to figure out the reachability to the rest of the network as well. We'll kind of click over different types of routers so that we can understand the impact that placing them in different parts of the network may have. Internal routers are, of course, routers inside an area. Usually, for SPF, we just consider an internal router a router that is not in Area 0, so any other area. In ISS, I'm going to say internal router is a router that is a level 1 router only. It, of course, only has information about the local area. And to get out, it just finds the closest level 2 router, looking, of course, at the attached bit in the LSP. Backbone routers are routers that are inside the backbone. So in SPF, routers that are in Area 0. They, of course, have not only information about their own area, about the backbone in this case, but they have information about the rest of the areas through, in this case, summary LSAs. And for ISS, the backbone routers are, of course, the routers that are only level 2 routers. Border routers, they're routers that connect to 2 or more areas or levels. So in the case of ISS, 2 levels, of course, level 1 and level 2. So those are the border routers in ISS. And in OSPF, they're, of course, the area border routers, where, as I said before, you can have more than one area, or more than 2 areas, actually, in an ADR. And then you, of course, have the AS border routers. In ISS, any node can pretty much be an AS border router. In OSPF, any node that is not in the stub area can be an AS border router. And all an ASBR does is it redistributes or inherits or learns routes from another domain and puts them in the local ISS or OSPF network. So this is a quick example to show how routers that are level 1 routers are going to look in the level 1 LSP information for the border router to know how to get out of their area. Information that comes from other areas, in this case 10.1/16, is originated in a different area. The level 1 LSPs get to the border router translates that or builds a level 2 LSP that goes across backbone, and on the other side, you don't get anything on level 1 area. That is the default behavior. You rely then again on the attached bit to know how to get out. This is the same thing as before. We have the attached bit at the borders. The difference here is we have a couple of exits in one of the areas, and we have 3 areas in this case. We have an LSP that is originated. The LSP flows to the borders, and level 2 injects that information into the backbone. Always level 1 information is put into the level 2 backbone so that all the level 2 routers or nodes know how to get to everything in the network. Again, one of the functions of the backbone is to provide complete connectivity to the whole network. We continue the flooding so that everyone has all the information. When, in this case, the level 2 LSB goes around the backbone and comes back to a different level 1, level 2 router, and of course, in this case, the information that comes from level 2 doesn't get put back into level 1, even though it's learned in a different router from the same area. This is because route leaking is not on by default in ISIS areas. This is, of course, one of the reasons that causes non-optimal routing in these types of networks. You don't have information about what is outside, and again, like in this case, you have 2 exits to get out of your network. It's just a picture of what an OSPF network may look like. You have backbone routers, internal routers inside different areas, ASBRs that maybe get information from different domains, and ABRs that are at the borders of areas between area 0 and any other area. So when you work with ISIS, there's of course always the question, well, should I build a level 1 or level 2 only network if I only want one level? When you do this, you kind of have to be a little careful. Cisco's default, every router defaults to level 1 and level 2. So if you want to create a level 1 or level 2 only network, you have to explicitly configure that on the router. If you don't do that, then what will happen is the router will run both levels, will run 2 copies of the same SPF, one for each level, which will result in the same thing because it has the same information. So all you're doing is duplicating the use of your memory and of your CPU for the same information. So usually what we tell people is if you're going to do this and you're going to build a network or you already have a network and you don't know what to do and you want either level 1 or level 2, you should start with level 2. Functionally, from the SPF point of view, they both run the same. They're both going to consume the same thing, so there's no difference. The advantage of having a level 2 network is that then it's easier if you decide to migrate to a hierarchical network later. It should be easier to add level 1 areas and to create border routers at that point than following the migration backwards from level 1 to a level 1, level 2 network. So it's easier if you start with level 2. So inside an area, you always have level 1 adjacencies, and between areas, you have level 2 adjacencies. If you have transit areas, you need level 1 and level 2 adjacencies, which is one of the places where you do have to have both. Of course, in this case, where you have a transit network, in this case, we have only 5 routers, it probably doesn't matter. But you want to make sure that your transit path always has level 2 enabled. You want to make sure that you think about all the possible transit paths, and this is a very common thing that we see when people build networks. They forget sometimes an alternate path. Again, we're going back to redundancy, where you might have extra links that you provision that are not normally used, so everything works fine over the contiguous level 2 backbone, but then if something happens to one of the nodes, you might now use an alternate path. And if those routers were not already running level 2, you might run into black holes or loops or other things in there. The biggest mistake is, of course, that if you have a router that only has level 1 neighbors, that the neighbors are in the same area, then it's very tempting to just make it a level 1 only router. But of course, again, if you want a contiguous level 2 backbone, that is not the correct approach. For SPF, the way it works is a little backwards than with ISIS. What ISIS does, again, is every area is stubbed by default. You have to do something about it, which is route leaking that I'm going to talk about in a second. With OSPF, areas by default accept everything from the other areas. So you have to actually configure something special to make him not accept everything. So of course there are several types of stub areas in OSPF. The regular stub area where you reject or you don't allow external routes to be in your area. The important thing with all the different types of areas in OSPF is that all the routers in the area must know that they're part of that type of area. So they all agree on the optional parameters they exchange. So stub areas, no externals, totally stubby areas means no information at all from other areas. In this case, you don't accept externals or summary routes from the other areas. All you have is a summary, or not summary, all you have is a default from the backbone indicating which is the exit. So that's probably the closest equivalent to the default level 1 area in ISIS. And then NSSA, which was a way to get around the fact that you can't have external routes in a stub area. So NSSA allows you to have external routes that are originated inside that area. And all we did for that was create a new type of LSA that's called type 7, which is exactly as a type 5 external LSA. The only difference is that it's called type 7. What happens in the NSA area is at the ABR, type 7s are translated into 5s, so the rest of the network sees the externals as what they are, type 5 LSAs. So just a quick example of what an NSA is. You get type 7s from a different domain, you have them in your area as externals. When they get to the ABR, they get translated into type 5s. External routes from other domains that are put into your network are type 5s. They don't get injected back into NSSAs. Of course, as I said, the normal behavior is to allow things into your area. One of the things you can do if you don't want to just become a stub area or a totally stubby or an NSSA area, you can just filter some LSAs. And that is, of course, the inverse of what I'm going to talk about next, which is route leaking. In this case, we're selectively filtering summary LSAs from the input from area 0 into one of the other areas, or vice versa. And the way we do this is, the configuration is very simple. We use a prefix list to indicate which networks or which summaries are going to be injected in or out of our area. So that way we can achieve some type of partial stubbiness, I guess, into our areas. For ISIS, as I said, the behavior is backwards, in that you don't receive anything by default, so you have to allow manually specific information. And that's what we call route leaking. So level 1, level 2 routers, if we want to insert anything, if we want to let routes that we learn from the level 2 back into a level 1 or into a specific level 1, we can use route leaking. We have to make sure, and this is probably one of the most important parts, that the level 2 learn route is actually being used, meaning that the route must be in the forwarding table to make sure that we avoid loops. There are actually 2 ways of doing this that we implemented. One is using an utility called number 135. This is done with wide metrics and specified in that draft for traffic engineering and ISIS and OSPF. And there's another way, which is using the normal IP reachability, LSPs 128 and 130. So what route leaking does is when a route is originated at level 1, gets put into the level 2 backbone, it gets propagated. At specific border routers where we enable this, we can let the information that came on the level 2 backbone be put into the level 1 area. On, of course, the level 1 LSP of the border router there. There's a special bit that is used, which is called the up-down bit, that is going to let us find out if the route that looks like a level 1 route, by all means, was injected from the level 2 or not, if it was leaked or not. What it helps us do is that when the route comes down and gets propagated across the level 1 area, if it gets to the other border router, it doesn't get leaked back up. So it's very important to avoid loops. It's very important to avoid that level 2 might think if we leak the level 1 leak route back into level 2 might think that the destination is down here, not over where the destination actually is. So that's what the up-down bit is for. So the same thing, we originate a route, we propagate it to the level 2. If we leak it, of course, the up-down bit is set. And only where we leak it is that the routes are propagated. In this case, even if we had leaking configured at this border router, one of the conditions that I mentioned before, which is the level 2 route must be used, is not satisfied. In this case, we would have a level 1 route that we learned from inside the area, and we have a level 2 route that we learned across level 2 backbone in the same router. Level 1 routes are preferred in the routing table, so we use that one. That's why the level 2 route is not leaked back into this area. This, of course, has continuous connectivity. So again, the up-down bit is used to prevent that leak routes are re-injected back into the backbone and potentially cause a routing loop or something along those lines. Every time that the route is leaked, or the only time the route is leaked into the level 1 area is when the bit is set. So this is, of course, a function of the border router. And they're never propagated back up. With the 128 and 130 TLVs, what we do is we borrow one of the bits that are part of the TOS field, the one that is called the default metric, and we use that one as bit 8 to signal the up-down bit. This works fine, but there may be issues with not understanding that that bit is being used for this specific function. So, of course, the recommendation is to use the TLV 135, which is what works with wide metrics. And in Cisco routers, the way you enable that is by just using the metric style wide command in your router. So you want to always use areas where necessary, and you want to definitely summarize where possible. You want to, as we already saw, try to keep in mind not only the hierarchy, the opportunities for summarization, but also the redundancy that you may have in your network to decide if you need to summarize or not. We went through some methods, from route leaking to LSA filtering to an OSPF that uses different types of areas to stop different types of information that can be used if you want to only partially filter, partially allow some of the information in. And another part that is very important is you always want to define the backbone routers first. Again, if you're running in a one-level ISIS network, for example, you want to define level 2 to be present in all your routers. That makes it easier if you later decide to migrate to a two-level network. If you had an OSPF network that you start building, probably the best idea there too is to put your routers in the backbone in the area 0. That way, when you need to add areas or you need to start converting into a hierarchical network, it's a lot easier to do that if you start with the backbone. Of course, the biggest question is, well, do I really need a hierarchical network? And this is probably the biggest question because a lot of us are used to seeing a one-level ISIS network. Part of this is, of course, because of the fact that from the beginning, all areas were stub areas. So there was no other choice than to do that. The decision of going from a flat, one-level network to a multi-level network is not necessarily a straightforward one. It depends on many things. And of course, the two biggest things that it depends on is, of course, the size of the network. How much information do you actually have? And are you going to benefit by maybe summarizing some of that information? You can look at your routers, tell the impact that the size is having on your SPF runs, for example. And the other part that is very, very important is, of course, stability of the network. I said before that by using areas, you can hide or isolate some of the instability. So one thing that I want to make clear is using areas is not a solution for instability. Right? Hiding instability behind an area is not, you didn't fix it. You should go fix that. But multiple changes in your network, which might not be one unstable link, but just normal changes around the network, are going to cause multiple runs of the SPF algorithm, flooding around the network, etc. So you want to take those things into account before you decide to go from an all area 0 network or an all level 2 network to a hierarchical network. So we're going to talk a little bit now about detection and propagation of changes. Now that we talk about hierarchy, I learned how to maybe isolate the changes. I learned about how to constrain the scope of the SPF that we need to calculate. Well, the next part is, that's very nice. We have a small area or a small network. Well, how fast or what are the issues that are going to help me or not in detecting the changes and propagating them around my network? It doesn't matter that the network is small if I can't get the changes around fast enough, right? So some of the dependencies are, of course, detection of a link failure, things like change propagation, and of course, SPF computation, both initial weights and the time to run, the SPF that it actually takes. A lot of these things go back to what I was talking about at the beginning with fast conversions and stability. You want to have a balance between the two. Aggressiveness in detecting link failures in the flattened link may cause you to calculate more SPF runs, which generate more LSPs than you actually had to. So that may be counterproducing. So there are some methods that you can use to detect failure in a link. The router, of course, is a link state protocol, so you keep track of and save your links. And when the link goes down, you send the new LSP or LSA, indicating that. In some cases, especially point-to-point links, that is aided by the actual layer 2 protocols that may and sometimes indicate that there's a loss of the layer 2 faster than the layer 3 protocol. So you have to lose layer 2 hellos to know that you lost something. Or in cases of networks like ATM or even frame relay, you can have end-to-end detection or keep track of the end-to-end state to figure out if your remote neighbor failed. Probably a lot faster than you can using the regular hellos that you exchange. In LANs, however, it is not easy to detect all failure modes. Especially if you have a switch in the middle and the other side of your Ethernet fails, you don't know. You have to wait until your hellos expire. Talking about hellos in ISIS, the IAHs, or the intermediate system to intermediate system hellos, they contain the hold time. So that allows ISIS to determine how long it's going to wait, and then you can send hellos accordingly in that hold time. The minimum hold time that you can actually define currently in ISIS is 1 second. So that's how fast you can actually detect that your neighbor went down. With OSPF, the OSPF hello packets contain not only a hold interval, but they also contain a hello interval. And it turns out that the lowest you can actually set it to is 1 second for the hello interval. So that means that if you use 3 hellos as your dead interval, you might have to wait 3 seconds to detect the link is down, or that you lost your neighbor.
Has there been talk of the effects, the benefits of lowering a sub-second, and is that happening? Are they important?
So the question is, hasn't there been talk about sub-second hellos, and is that going to happen? Yes, there has been talk. There's at least one proposal that I know of for ISIS, sub-second hellos. I know of other people who are trying to do the same thing for OSPF. Is it going to happen? I don't know. It's going to happen. In my opinion, and that's what I have in the next slide, there are definitely advantages to using fast hellos. And the main advantage, of course, you detect the failure faster, right? Probably the main disadvantage that you're going to find is that you need more resources. More bandwidth, more CPU, more buffers, because you now need not only send hellos faster, but receive hellos faster. Depending on the number of links and number of routers and et cetera that you have, if you do want sub-second convergence, and we might be talking about 300 to 600 milliseconds, you need to send hellos every 100 millisecond per interface, and you have 100 interfaces. That means a lot of hellos. You need to send and receive. So that is probably the biggest disadvantage in using fast hellos. For point-to-point links, usually this is not an issue, because again, sometimes you can detect layer 2 failure, you can detect that the light was lost a lot faster, you can actually send a hello in some cases. Depends, of course, a lot on the platform that you're using, the OS, whatever. Most of the problems, I believe, are going to be on multi-access LAN segments, mainly, where you can't detect that your neighbor failed. So it's going to happen, I don't know. Does anyone else know? Does anyone else want to guess? Yeah, good. So going back to how the protocols currently work, which is what we have to deal with today. When and if we ever get fast hellos, then we can worry about that. So for SIS, as I said, the minimum hold time that you can actually do is 1 second. In the Cisco router, the way you configure that is just put the minimal keyword in there. And what that does is it waits for a second, or it sends hellos with a hold time of 1 second, and the hellos are sent according to another variable in there, which is called the hello multiplier. So usually it's like 3. So you send hellos every 300 milliseconds. So the fact that you're sending hellos in sub-second times, it doesn't mean that you can have sub-second convergence. Right? You still have to wait for a second, in this case, to detect that your neighbor is not there anymore. In OSPF, the way you can configure or modify this is using the IP-OSPF hello interval and dead interval commands to change what the router actually advertises. By default, and I've never figured this out, OSPF uses a dead interval that is 4 times the hello interval instead of 3. That seems to be the norm and everything else. So you can configure this if you want to things like 1 second and 3 seconds. But again, in OSPF, it's going to take a lot longer because you can only send hellos as fast as a second currently. In OSPF, in ISIS, there's an added issue, which is the fact that hellos are padded. Hellos are padded to the MCU size. This is a good thing because it helps you detect MCU mismatches. So if I send you hello and you never receive it, it probably means that your MTU is smaller than mine. It's very easy. Usually, networks don't change their MTU in the middle of the day after you've already brought up your session. So you don't necessarily need to keep padding all the hellos that you send. Well, detecting MTU mismatches is a good thing. Sending padded hellos may not be such a good thing because you have, of course, insufficient user bandwidth. The hello is generally a small packet, and your MTU may be big, 1/2K, 4K, depending on the length that you have. It, of course, means significant number of buffers, not only to send, but also you have to receive all the hellos that people send you. And processing overhead if you use authentication. This is because the authentication hash is calculated over the whole PDU, so you have to calculate it over the pad. So if you have a smaller packet, it's a lot easier to process all that. You can get rid of it with any of these commands by interface, by type of link, the whole router, however you want. If, at least on a Cisco router, if you get rid of it, it doesn't mean that you don't use it. You use it to negotiate the adjacency at the beginning to make sure that you have matching MTUs, and then after that, you forget about it. So the only time when it's actually useful is, again, assuming that the MTU is not going to change in the middle of the day, is when you establish the adjacency. After that, in normal network, the MTU shouldn't change, so we don't need the padding anymore. So after we actually detected either through hellos or through layer 2, some type of layer 2 indication that our link is down or that our neighbor is not reachable anymore, now we need to worry about propagating the information. So we need to propagate an LSP or an LSA, depending on the protocol. There are different reasons why you would do this, send a new LSA or a new LSP. One of them is, of course, when the adjacencies come up or down. You have new neighbors, new interfaces. Interfaces go up or down. You have new routes that you learn. There's routes from other areas that change. Of course, this is true at border routers, so you need to update the information in the rest of the network, for example. When you change metrics, this is a good one because if the metric changes, there's a possibility that the tree changes to which you're going to go. Almost any configuration changes, and of course, periodic refreshes. Now we all know that in ISIS, periodic refreshes can take up to 18 hours or are done up to 18 hours. And with OSPF, except in some cases they're done about every half an hour. So usually the process is you create an OSP, you put it into your own database, and then you flood it. You send it to all your neighbors, they get it, they put it into the database, and they flood it. And that keeps going on and on through the whole network. So it's important, or it may be important, to control the frequency with which an LSP is generated. Now, for example, in ISIS, you generate one LSP for the whole router, and that LSP includes all the information that you have, meaning information about your router, information about external routes that you may be redistributing in that router, etc. So if you have a link that is flapping, you probably want to make sure that the information gets propagated, but you don't want to be too aggressive. So you can control, if you want to, the interval of LSP generation by default is 5 seconds. So it means that if there's a change, you send it, and if there's another change before 5 seconds, you have to wait. This, of course, to increase the stability of the network, to try and not propagate too many changes around, because we know that every time there's a change inside the area, we need to go and calculate SPF. With OSPF, until I get to some slides a little later, there isn't really a way to throttle the LSP generation. Of course, we already detected, we sent the LSPs, and now we have to do something with the information that we received or that we have. That, of course, is where the Dijkstra algorithm comes in, and we have to find what the shortest path tree is for the network or the area that we're in. From the information that we get by running the SPF algorithm, we end up with routes in the routing table. There are many things that Dijkstra algorithm depends on. Usually we think, okay, it's based on number of routers and number of links, because that's what the algorithm actually looks at. But the complexity may be a little bit. Okay, so I'm going to stop here for a second while they change the tape. The algorithm itself depends on the number of routers and the number of links that you actually have. But in reality, there are a lot more things that you have to worry about. Of course, there's the number of links is important. There's bidirectional check. So the number of routers is important. The stability of the adjacencies, the frequency of the SPF, the number of level 1, level 2, and both levels, number of areas that I actually have, et cetera. All that influences the actual CPU usage, the actual resource utilization of the algorithm itself. So of course we're running this on a real network, so it's not anything isolated anywhere. Route installation sometimes may be expensive. So this is not only run the SPF and that's it, you have a tree, but now you have to install the route somewhere, compare it to other protocols, et cetera. And of course, flooding has to also happen when changes are detected, propagated, received. Usually, SPF is event-driven. That means you have to wait for a change before you do it. Otherwise, there's no point in doing it. While flooding may happen a lot more. Meaning there are some changes or some flooded packets that you receive that actually cause no change, like when you do a refresh. So you, of course, don't have to run SPF at that point. So you can try and control the pacing of some of your events, like the LSP generation, like the SPF computation, for example. If you slow it too much so that your network becomes stable so that you don't react too fast, then that's good for stability, but it's bad for convergence. If you react too fast, it may be good, maybe not. It may be good for convergence, but it may actually lead to other problems, like constant flooding or constant running of SPFs, et cetera, that may lead to high CPU utilizations, meltdowns, whatever. So exponential backoff, which is something we do in routers, is kind of a compromise. Is a way that we have to react fast to the first event, and then if there are successive events close enough, we're going to be a little more conservative with those. So there are three things that we take into account when we talk about our backoff algorithm, about how we implemented it. There is, the first one is, of course, the initial delay. This is the timer, the time that we're going to wait between the event happening, which may be a link changing state, and the time we're going to act. So a link changes state, and we're going to now generate an LSP. That's the initial timer. Or we receive an LSP from someone else, and we know we're going to have to run SPF, so that's the initial timer, between the time we receive it and the time we actually do something about it. Then there's an incremental interval, which is, okay, I received the first one, I waited the timer, I did whatever I had to do, and now I received another change, let's say another LSP. So how long do I wait? So we want to wait incrementally as changes happen. Again, the idea is to act quickly at the first change, and then to wait a little longer as changes keep occurring in a short amount of time.
If you're talking about SPF being event generated and this occurring on flooding when you're running through LSP synchronization, it's better to do this sort of thing on the router that's actually going to be sourcing the LSP or LSU, depending, whatever. talked a long time ago, we kind of started a conversation with Ashley about this, and I know that a bunch of vendors were working on it. Having some sort of decay-based back-off for link level events would be much better. And I've been waiting for it for a very long time.
So the comment is, if you use a backup algorithm in things like SPF, you may run into, and maybe the flooding or the propagation of the LSPs that you receive, depending on when you run the SPF, you may run into synchronization issues with your database. Because maybe my timers are different than the other guys' timers, so the routes just don't match at some point. You know, the databases don't match, the run tables don't match. Yes, that is correct. So the comment is, you are probably better off if you take care of the back off, or let's call it the dampening, at the source. So if I'm the source and my link is flapping, well, I should probably be the one who generates my LSP or not, so that everyone else can have a consistent table. Yeah, that's true. So what we can do here with exponential backup is two things. We can do LSP generation, which is kind of that, kind of, not exactly. But is if the link flaps, I'm going to advertise the change in the first LSP as fast as I can, or fast, and then I'm going to wait. We also provide some knobs for you to do SPF backup algorithm. As any, well, maybe not any vendor, but we will tell you. Here's a rope. Go do with it whatever you want. So you have to be very careful.
This is kind of a future scramble as we
correct.
Sub-second.
No, I agree. Now, the other comment that you made is if you do kind of interface dampening, that would help a lot.
Yeah.
Yes, it would. Talk to me after we finish, and I can actually give you something to test. So the initial delay, you have the incremental delay, and then the maximum interval. So you have the initial delay, again, is how fast after the change I want to react. The incremental delay is how long after successive changes I want to wait. And the maximum interval is, well, the network kept flapping or something kept happening, and this is the maximum I'm going to actually wait. So we don't want to increasively wait, because if there's some stability somewhere, we might just going to keep delaying convergence. So there's a maximum interval in there. So here's some default timers. By the way, if you don't have the slides, they're off the NANOG page. So you can go download them and look at the timers later. The way this works is, there's a syntax. And I'm going to do the example with the SPF, knowing the comments, because that's what the slides say. So with ISS, we do this with this command called SPF interval, and we have basically three variables. This is what the variables mean. We have maximum time, there's a maximum interval. We have the initial time, the initial wait, and C is the interval, the increasing interval. So in ISS, for whatever reason, kind of felt like that, maximum, initial, and incremental. In OSPF, the way the CLI worked is initial, incremental, and maximum. Whatever makes more sense to you, you can do either one, depending on the protocol. So the way this works is, I also have to remember. So the way this works is, for example, for ISS, if we configure this, SPF interval 10, 100, and 1000. So 10 is in seconds, and this is the maximum time that I'm going to wait, 10 seconds. 1 is the initial delay, so or 100 is the initial delay, this is in milliseconds. So I'm going to wait 100 milliseconds the first time. And then 1000, which is in milliseconds, is the incremental delay. So that means that the first time something happens, in this case, an SPF event, I'm going to wait 100 milliseconds and run SPF. Then if something else happens, I'm going to wait a second, right, 1000 milliseconds. And then I'm going to increment that until I eventually get to 10 seconds. And that's the maximum we're going to do. So the first time I wait 100 milliseconds and I run, then if I wait at least 1 second, and if I need to run SPF again, then I run it. Then this is kind of called exponential because I don't wait another second, but I wait 2 seconds to run the third SPF. If this keeps happening, I then wait 4 seconds, then I'm going to wait 8 seconds, and then I'm going to wait 10 seconds. 10 seconds is, of course, the maximum. So even though the next step was 16, I'm going to wait 10 seconds because that's the maximum I'm going to do. If changes keep occurring, I'm going to keep waiting 10 seconds until the network is stable. So we consider the network stable is when we go over 2 times the maximum interval, 20 seconds in this case, then we go back to the original trigger. So what that allows us to do is, in the first change, it lets us react faster to the change. And then we increasingly wait until we wait the maximum, and then we stay at the maximum forever and ever, or until the network is stable again, in this case, again, 20 seconds. This is kind of the same example for OSPF with the same timers, but of course remember that the order of the timers or the order of the numbers is different. So in this case, this is the initial wait. This is incremental wait, and this is the maximum wait. So for this configuration for OSPF, what I would do is the change happens, I wait 10 seconds, run SPF, and then I wait up to, or at least, 100 milliseconds, and then run it again, and then 200 milliseconds, 400 milliseconds, 800 milliseconds, until I get to, in this case, 1,000 milliseconds, which is 1 second, of course. And so after that, I have to wait till the network is again stable, in this case for 2 seconds, 2 times the maximum interval that I configured, and then I go back to the initial trigger. So if you notice, and you have to be kind of careful about this, because, and don't blame me, I'm not responsible for the CLI, even if you put the same numbers in the same order for what seems the same command, they act differently, right? So if you run a network with only ISIS or with only OSPF, you shouldn't have a problem because all you have to do is learn one thing. But if you ever are in a situation where you have to, jump back and forth or something, then you have to, remember that the order is a little different. And the results are significantly different. In the first case, with the same order of numbers, we waited a maximum of 10 seconds. In this one, we waited a maximum of 1 second. Right? So you have to be a little careful. Of course, the most important thing that I can say is use this with care. This has been out for a while, and to be honest, I don't know if other vendors actually do this or not, but I'm assuming if they don't already, they're not far behind. Each network is different, so what might work, or what the examples might say, may not actually fit in your network, because the stability patterns or the size of the table or the tree may be bigger or smaller in your network. So one of the things that you always want to do before setting these timers specifically for SPF computation is find out how long it takes you to normally run SPF. Right? So you want to make sure that the initial delay is longer than what it takes you to run SPF. If it takes you 20 milliseconds to run SPF, well, you don't want a timer of 10 seconds, right? Because you might not finish before you start. So you have to be also careful about other things, which is stability of the network, for example. If you have a network and some link in the network fails, there's a two-way check on the links. So if a link fails, basically you only need to receive one of the 2 LSBs to know the link is not available anymore. You don't need to receive both. But in the other case, which is when the link comes back, you now need to receive both LSBs to know that the link is available. So it might take a little bit longer to learn both LSBs than to learn only one. So you want to be also thinking about that, so that when you configure your timers, if you configure your timers, you account for that somehow.
Are there any commands internally?
like come up and say, yes, what calculation was done, hold that time and actually done that.
Yeah, the question is are there any commands that, at least in Cisco, let you see how long it took you to run SPF? Yes. There's something called show ISIS SPF log that shows you that, and there's something equivalent, and if I'm lying, someone's going to correct me. I think it's show IP OSPF stats. Good, so we're all lying. Great, sure. So it shows you there. The other thing that it shows you, which is very useful, is why the SPF was run. So, you know, it might tell you that it's because of some specific link or, you know, some specific LSP or LSA that you're receiving. So, this is, again, for OSPF, the syntax. So you first have, again, the start, then the hold, and then the maximum, which, in my mind, it makes a little more sense. You want to know which one is the first one that you do. And for LSA throttling, which before, about 5 slides ago, I said that you couldn't do it with OSPF. You can now using this. So you have the same thing. You have the initial delay the whole time and the maximum wait. As someone commented here in front, it's probably a better idea if you're going to use one of these to start with the LSA generation than with the SPF. The SPF may take a little more coordination because you want to make sure that all your routers do it. Yes?
You go one further and abstract that to which you do not think.
Correct, and the comment is that, yeah, this is kind of nice if you want to do dampening kind of per protocol, but you can actually do it per link. So you could implement, or you could get a router from a vendor that does dampening at the link layer, so that the interface is actually flapping and you have 20 protocols running on that interface. You don't need to have something like this enabled for every protocol, but you can have layer 2 actually tell you what's happening. And for ISIS, remember that the order is a little different. Initially, we put the maximum, then the initial wait, and then the incremental wait. The reason why the syntax is different is just because of backwards compatibility. That the CLIs were different to start with, so they're different now. So we can do SPF interval, we can do the PRC interval as well. In OSPF, we don't need to control the partial SPF calculation separately, because the SPF, the timer's SPF command controls that as well. And then we also have the LSP generation interval in there. Just a few more knobs that you can tweak. If you use the exponential backoff, you kind of, again, dampening, yes, better if you do it at layer 2. You can do it at layer 3. This should prevent you or help you by reducing the amount of flooding that you need if there are more and more increasing changes in your network. So one of the things that you can do is, by default, LSP pacing is 33 milliseconds. So you can send an LSP every 33 milliseconds if you're flying. So if we assume that this type of backoff is going to help us avoid large number of floods, then you could reduce the timers for LSP pacing and send them out faster. So just something you can do with LSP interval in there. Other things for SPF that you can play with. One is the use of this command IP SPF flood reduction, which allows you to set the DNA bit on all the LSAs that the router originates. The DNA bit is the do not age bit. So what that means is that the LSAs might never age out, so you never need to refresh. So remember, by default, OSPF has to refresh, or refreshes about every half an hour. because the maximum time to live is 1 hour. If the LSAs don't age, then you never have to refresh them. And you can also adjust the pacing of the LSAs. If you do flood periodically, you can use the group pacing, LSA group pacing command to pace or to distribute the flooding or the updating of the LSAs across, let's say, the half an hour period, so that not everything is flooded at the same time or refreshed at the same time. This, of course, the most important cases where you have routers that have a lot of LSAs to flood. Routers that may have its own router LSA, that may be DRs on several links, that may have especially a lot of external routes to redistribute. And really you have to generate type 5s for every network that you have. Just some more commands for, again, pacing of the LSAs. Again, the range is 33 milliseconds. It's also configurable between 5 and 100 milliseconds. For flooding and for retransmission of the flood. There's also the retransmission of the normal LSAs that you propagate, things that you may be announcing. So you can configure that as well. Okay, so I'm going to change almost completely and talk about just other things that are going to help scalability, convergence, etc. One of them is the use of the overload bit. This is defined in one of the ISO documents, and it was intended to indicate that basically the router is sick and it can't forward packets. So it's overloaded. So the intention was the router can advertise its own LSP with the overload bit set, which means don't use me for transit. Connected prefixes, IP prefixes, which are the ones we care about here, are still reachable, but only the connected ones. So this means the router is pretty much taken out of consideration as a transit when calculating the tree. You can set for ISIS the overload bit manually if you want to, so that you can, at some point in time, just decide that you don't want to use this router anymore. It's useful if you're going to maybe upgrade your router, then you can set the overload bit and take it out of the tree before you actually turn it off, for example. Or if you have some routers that shouldn't be in the network, like a lab router, then this is a good use for that. So you have a simple network like this one, where the normal path would have been from R1 to R5 to R4. If R5 is set with the overload bit in it, then router 1 won't use that path to get to router 4, but it'll go what it looks like the longer path all the way around. So it is useful, again, to use it when you can't forward traffic to all the destinations. Some of the specific cases is when your IGP, ISIS in this case, may have already converged, but other protocols that are going to provide additional information for forwarding may have not. This is specifically the case of BGP, for example, or maybe even MPLS if you run that in your network. But BGP is going to take a lot longer to converge than ISIS is. So if you're an ISP, which I assume most of you are, you need the BGP routes to be able to forward across the router. Even though the router may have already reachability to all the next hops, etc., it doesn't have reachability to the BGP routes. So that is a good use of this. So you can set the overload bit, for example, after a reboot, and then allow BGP to converge. BGP will signal, or should signal, when the convergence is complete, so that ISIS can unset the overload bit, and then traffic can go through the router as normal. You can configure the timer. Depends on how many neighbors, how many routes, et cetera, that you have. Usually the timers that people use are between 2 and 5 minutes. So what would happen is the router boots, When the local LSP source or is originated, it's sent with the overload bit set, so no one uses it for transit. Once BGP converges, and we know that the router has all the transit routes, then the overload bit is unset, and we go back to normal. So this is what the syntax looks like. You can just set it, and that's it, it's set. Again, this is useful if you're going to take the router out of service, for example. You can set it on startup and put some value of seconds that you want to wait. Or you can set it on startup and wait for BGP. The default time for the wait is 2 minutes currently, which may or may not be enough for BGP to converge. Now, it depends again on the type of router that you have, the number of BGP sessions, the number of routes you're going to learn, whether this time is going to be enough or not.
What is the wait for BGP trigger? What is the trigger for that?
The question is, what does the wait for BGP trigger do? What it does is, when you bring up your BGP session, the way we do it is the router goes into this read-only mode, so it only accepts routes. And then after a while, you know that your neighbor's finished sending you routes through an indicator that we use, which is currently a keep alive. But it will eventually work with what the restart draft talks, which is the NMT update. So you get the indicator that says, I finished sending you all the routes. When you get that from your neighbors, you can run the best path selection, and that's it. Of course, you do that for the same reason you don't want to run SPF too often, which is if you run the path selection in the middle of the updates before you get everything, then you might not have run all the paths, and you might think you converge on a specific path, send it to your neighbors, et cetera. And then when you actually get the new valid paths, you're going to have to advertise again.
There's obviously a danger there. Not in implementation we're discussing, because you have to wait for the second keep alive anyway, but updates take place in the keep alive, so.
Yeah, if you code it correctly, it'll work. Yeah, shouldn't matter. This is just a different interpretation of what the message actually means. Correct. In any case, so that's what wait for BGP does. It waits until the neighbors have converged, which is signaled by either a keep alive or eventually an empty update that tells us that all the neighbors or the specific neighbors finish sending us the updates. When we get quorum or whatever, we just calculate the best path and we signal the internal protocols. You can also use this on MPLS networks, for example, where you, of course, need the HTTPs to have converged first before all the labels are distributed. So you might want to set that. And some timer, nice timers, maybe 120 seconds. For SPF, we can do the same thing, or not the same thing, but something similar. SPF, of course, doesn't have an overload bit and doesn't have any extra bits that we can use. So we can kind of have the same functionality by using this command, which is kind of similar. It also has a wait for BGP little keyword there. And what it does is it advertises the router as a stub. So it basically sends a metric of infinity in the LSAs. So it gives the effect, it kind of gives the same effect, where your connected networks are reachable, but you shouldn't be used for transit. OSPF has a little twist there, which is that infinity doesn't really mean that you can't use that link, because if that happens to be the only path, if this router that we're using to advertise the stub was the only path to the destination, even though the metric is infinity, OSPF would choose it. So of course, this works if you have redundancy in your network, which is the only reason you would be doing this. If you didn't have redundancy in your network, then who cares if you lose some packets, because you're going to lose them anyways.
Overload speed on the wait for BGP critical packets?
The question is this Cisco proprietary or not? The overload bit is standard. We just have been using it like that for a long time. There's actually a draft that was published to document this, the overload bit. I don't know what the state of the draft is, but it's out there somewhere. The advertisement in OSPF is a stub. I know we do it. I don't know if anyone else does it. There is an informational RFC already published on this, so anyone can do it if they want. When you build, and this is what I said, when you build an LSP, you of course include all your adjacencies in your LSP. And this of course includes parallel adjacencies. But when you build a tree, you only use the best link to calculate the tree. So you know, in reality, you don't need to include all the parallel adjacencies on the LSP, only the best one. There are some advantages to doing this. One of them is, of course, that the LSPs are going to be smaller. Depending on the number of parallel links that you have, this may actually be significant. You, of course, have a lower chance of the LSPs being fragmented. Of course, in ISIs, you can't fragment the LSPs anyways. And assuming that you have a consistent MTU across the whole network, this shouldn't be a problem. But, you know, in any case, it reduces your chance of finding a link that actually has a smaller MTU and not being able to propagate it. SPF calculations are going to be more efficient because you have to deal with less links. You have to eliminate less links that you actually don't need. And if you have a flap in one of the parallel links, then that's basically invisible to the rest of the network, as long as the best link is not the one that flaps, of course. So if you have something like this, you would send your LSPs out. You would send your LSPs, and if you look at the LSP from B, you basically have two links pointing to A, one of them with a metric of 3 and the other one with a metric of 4. And the same on the other way around. You look at the LSP from A, you have two links advertised to B. Well, you really don't have to do that. You can eliminate one of them. This is a problem if you're doing traffic engineering, because you actually want to have knowledge of both links. You want to do this. So the way we get around it is if you enable traffic engineering in your router, we advertise everything. Well, when you get on LANs, this becomes a little bit hard, because even if you really have a point-to-point adjacency, meaning two back-to-back routers over Ethernet or GigE or whatever, you really can't advertise it as a point-to-point. You can't get rid of the redundant links. The reason for that is, of course, you have a DIS, and everyone in the LAN is not peering or not adjacent to the other routers on the LAN, but they're adjacent to the pseudonode. So the LAN topology, if it looks like this, your actual logical topology looks like that, where you have the pseudonode and everyone is peering to the pseudonode itself. So in reality, this is not really logically a point-to-point link. But if you configure the links with that command, ISIS network point-to-point, for multi-access networks like LAN topology, then what the topology, the logical level is going to look like is like a point-to-point. So this, of course, requires less steps in the computation because you don't have to go to the DIS. You just go directly to the other guy. Of course, there's no DIS election, because if there was, then it would defeat the whole purpose, right? You would end up with a pseudonode anyways. And there's no CSNP flooding, just like the DIS does on the regular LAN, right? Every 10 seconds you send CSNPs. So we changed that behavior a little bit to allow you to create point-to-point adjacencies over LANs. This is sometimes common depending on the application that you have for your network. Any questions up to now? Nope. Good. Yes.
I realize it's dependent on stability of the network and size of your network. Do you have any best common practices worth sharing of implementing higher speed than 90 for, or when you need to between areas? I mean, I've heard numbers of X nodes. When you obviously look at utilization,
yeah, so the question is, when do you actually need to start implementing a hierarchy in ISIS, or when do you really need areas in OSPF? Is there a magic number? No. Yes, it depends on a lot of things: the size of your network, the stability, the actual number of routes, the topology itself is different to run SPF. If the topology is wide or narrow or long, deep, whatever. So it depends on a lot of things. So no, there's no magic number. We've seen very big ISIS networks of up to maybe 1,000 nodes. That doesn't necessarily mean that OSPF can't do 1,000 nodes, right? It's just how the network was built. But even at that point, they're not necessarily to the point where they have to have a hierarchy. They might want to have a hierarchy to reduce the size of their SPF tree, the calculations they need to do, things along those lines. But they're nowhere close to the border where they need to be. A lot of it might be administrative decisions in some cases as well. So just to put the other side, I haven't seen an OSPF network with 1,000 nodes, but we've done an OSPF network with 1,000 nodes. Of course in the lab, but close enough.
I have another question, so maybe related to that. So we're talking about the result from NANOG to do some tuning with allow the program of the holding server. I just wonder, how much ISP is spending in this kind of configuration in the real production network? So is it widely used, or what's the percentage of the cost?
So the question is, you can tune the hello parameters, the hello interval, the hold time interval, to make it converge faster. What's the percentage of people who actually do that? No one. One person. No, I guess it's...
OSPF summarization, like what you do seems to be dangerously close to a distance vector protocol. So do you see anything bad by this summarization?
You mean between the areas you do kind of a distance vector protocol thing? Do I see anything bad with that?
Yeah.
No.
No, but what happens is like areas are also connected directly in addition to being connected to the backbone area.
Oh, so that's kind of a thing that shouldn't happen. So depending, see, hierarchy in OSPF and ISIS, even though there are ways to get around it, and it's kind of strict. You have to be connected to the backbone. So backdoor connections between area 1 and 2. There are some alternate ABR implementations that you can get away with, but according to the spec, no. So it depends. There are some cases where you can do that. There are some things, if you go read like the ISI spec that talks about partition healing and things along those lines. Things that yes, if you do route leaking and you manage it correctly, you could connect to level 1 areas with a fake level 1, level 2 router in the middle. But let's say those are not necessarily common practices. It doesn't mean that people don't use them sometimes, but not necessarily common practices.
So auto summarization, which is still in there, but it's only classical. It's my understanding it's only classical. Is there any chance that some other sort of auto summarization based on lighter routing would come into play?
The question is, auto summary is usually classical. Is there any chance that we'll ever implement a classless auto summary, maybe based on the contents of the RIB or whatever, and summarize that way? Yeah, there's probably a chance. Whatever that means. So there may be advantages to doing things like that, in that if your auto summary depends on network boundaries. Unless you necessarily have all the information, you might not be able to summarize correctly, meaning you might end up with halts, right? So that means that if auto summary is castful, you won't be able to reap all the benefits of summarizing your table, whatever the table is. But if you did it based on other things, like the actual contents, it probably depends on the actual protocol and the actual place where you do it. For example, if you do it as an ABR and OSPF, it might be straightforward. If you're talking about bigger tables like the BGP table, you might have to worry a little bit more about it because you have the whole path. And do you want to aggregate? Do you care if they came from different providers? Do you not care? What do you do? So that's a little bit trickier.
I have another question. It might be our scalability is not the OSPF either. So my question is, when we implement the MPLS DCS, so at the edge, as a PD router, there may be the PD router will be connected to 100 customer networks, and each of them may run the OSPF or RIP file. So is there any scalability issue so we have a concern for scalability of the OSPF or any other solution for us to do that at the edge of the PD router?
So I'm not sure I understand the question, but you're saying that in an MPLS VPN network, you have a P router that might be peering with the customers using OSPF or RIP or something.
So right now we are running, if we have about 100 customers, each of them runs their own OSPF process, maybe
Correct. So that we don't veer way off the main thing, let's talk about that a little later, specifically the VPN case. And the fact that you need to, at least in our implementation, you need to run different processes at the border. That may be a scalability issue, but let's talk about that later. Okay, so I'm going to go into BGP. These are the things we're going to talk about. Of course, we're going to start with full mesh. So this is what the spec says, you need a full mesh. Why? Because you can't send information you receive from an internal neighbor to another internal neighbor. So the only way you can learn information that an internal neighbor generated or propagated or received into the network is if you peer with that. Very simple. You need a full mesh. One of the reasons I think, or we think, that this restriction was put in is because there's no way to detect an update loop in IBGP. For IBGP, you just rely on the AS path. For IBGP, you don't know, so you may end up with a situation like this, where you guys just send the updates around and around and around. Now, an update loop is not as bad as a routing loop, right? Because a routing loop means your packets loop. In an update loop, your updates loop. So assuming that the update has the same next hop, well, your packets are theoretically going to be forwarded to the right place. But, you still don't want to have that in your network. You have constant churn of your tables, you have constant changes, updates, whatever. So consequences of not having a full mesh, of course, are black holes and other loops. And sometimes, even with some of the deployed alternatives to full mesh, some type of update loops in general. There's only one little tidbit of saving grace here, is the fact that you really don't need all your routers to be fully meshed. You only need the border routers to be meshed with all the other routers. So if you understood this, you can do it. If not, don't worry about it. So there's some scalability concerns in IBGP full mesh. One of them is, of course, administration. It has nothing to do with technical ability of BGP to maintain the sessions or not. And this is the fact that if you have a full mesh of routers, for example, let's say you have 200 routers and you add a new router. Well, then you have to go configure 201 routers. So, this may become a pain to do. Other things you have to, think about is the number of sessions. You have to maintain not only the BGP session, but the underlying TCP session. So this goes by that formula, n-1 divided by 2. So this creates overhead. Even in a stable network, you might get up with tracks at the same time and, create some issue there. And then there's, of course, the BGP table size, which we all know keeps growing and growing. And the issue with a full mesh is that the more neighbors that you have that are generating views, the more views you're going to have. So if you have 10 border routers that you're a neighbor with and all of them are receiving full routes, you're going to have 10 copies of the full routes, assuming that they all prefer the external route over the internal route. Yeah, so that's something else you have to think about. Worry about the memory consumption. So there are some tools that we can use to make BGP networks more scalable. One of them is peer groups. They help with two things. One is the configuration size. As we're going to see in a second, they're going to let us group configuration commands that are common to neighbors in one place. And they also help, and this is the most important part, with the update, replication, and advertisement. So a peer group is, again, a tool that's going to help us apply the same commands to multiple neighbors. So you have 200 customers and they all get the same routes, they all have the same policy. So you can put them all in a peer group. The important thing here is that they all have to have the same outbound policy. That's why at the end we can reap the second benefit, which is update, replication, and advertisement. If everyone has the same policy, it means that everyone gets the same update. It means they only have to find the update once, instead of one time per neighbor. So let's say I have this very simple configuration. I have two neighbors, and if you note, they're both in the same remote areas. They all have the same exact configuration. So I can just configure them in a peer group. And the way I do that is I have a peer group, and I have the common parameters, the same ones that these guys had here, as part of the peer group, and then the neighbors are just members of a peer group. So you basically inherit whatever the peer group says. But of course, in a configuration like this, you save like 2 lines, which is no big deal. But if you had 100 customers or 200 internal neighbors or something along those lines, then of course the benefits are increasing down that way. So everyone must share the same outbound policy, because again, everyone's going to get the same update. So there are groups of neighbors that you can put in a peer group that are typical guys that you put in there. Router filter clients, for example, or IBGP neighbors. Now you don't want to mix IBGP neighbors and reflector clients, because remember that you don't reflect the same way, right? Routes that you receive from an IBGP neighbor, you send to your clients, not to your other IBGP neighbors. So you don't want to put them in the same peer group. You can have IBGP neighbors or EBGP neighbors. You can't mix them because, of course, to EBGP neighbors you have to prepend your AS and AS path, but to IBGP neighbors you don't. So, things like that. There's only one exception to the whole rule, and it is the next hop, meaning that the neighbors in the peer group can get different next hops. So that's okay. And we get away with that because right before we put the packet on the wire, we change the next hop of the update. So that's very simple. So what do people do? Usually, of course it varies from network to network, but there are 3 generally common accepted types of peer groups for customers, for example. Default route only, custom routes, full routes. So you have customers that come to you and say, I want partial route information from you, you just put them in that peer group. If they say I want full routes, you just put them in the peer group. Or if they say I want the default, you just make them a member of a specific peer group. And it makes it nice because you can just, in one place, put all your configuration without having to worry about having to repeat the configuration 200 times, one for each neighbor, and risking an error. So you can do things, of course, all the normal inbound filtering, RFC 1918, Class D, things that you are using, you don't want to receive them back. You want to maybe use max prefix to limit the number of routes that you receive, etc. So this is a simple example. This is the EBGP default peer group. It has an outbound route map that we assume the route map actually says only advertise the default. For the customer routes, full routes. If you look at this, they all have the same incoming filter. We want to filter the same things from everyone. We don't want anyone to send us private addresses. We don't want anyone to send us our own addresses, no matter who they are. Of course, behind there, you have the actual route maps that you apply. So, if you have things like lots of routes that you need to advertise to lots of peers, this is a very good solution to use peer groups. Because the update generation is only done once per peer group. So the alternative is you have 100 neighbors, you walk the table 100 times, and you send one update to each one, right? Or however many updates to each one. In the peer group case, instead of walking the table once per neighbor, you walk it only once per peer group. So you generate the update by walking only once, and then you just replicate the updates for each member of the peer group. So of course this means you can, your scalability is enhanced because you don't have to do as many, you don't have to do as much work, so you can theoretically support more peers. So as I said, without peer groups, you do it per peer. With peer groups, you walk it only once. There's a little trick here. You have a group leader, and what we do is we elect a group leader, we walk the table for him, or for it, and then we just replicate the same updates for everyone else. And of course, the trick for all this to work is that everyone needs to be synchronized with the leader. And what that means is that the updates that are sent to the leader I also must have sent to everyone else. So of course, there's a possibility that you run out of sync. If some of your neighbors are slower, or if one of the links that you're sending updates on is slower, or if for some reason you have a low TCP throughput, you're losing ACKs, whatever happens that causes you to not be able to uniformly send updates to your neighbors. It may cause you to get out of sync. Of course, what that means is that you're going to keep walking the table for the leader, but now you also need to walk it for the neighbors that are not in sync. So you lose the benefit. So you want to make sure that you address some of these things, and these are probably the most common cases. You probably can't do anything for the last two. The neighbor is busy doing something else. Well, unless you own that router and you can go configure it so that it doesn't do NAC or something else, then you can't fix that. The peer has a slower CPU. Well, their internal routers, yes, you can probably have uniformity in your network, so maybe you want to just take it out of the peer group and put it somewhere else. For their external routers, external neighbors, you can't do much about that. But for the other two things, like for example, slow TCP throughput, you can kind of fix that. There are many things, there are some things you can do about this. Or, for example, cases where you just get a rush of TCP ACKs. If you're sending updates to a bunch of neighbors, they might all just ACK at the same time. And we're not even talking about the case where they're sending you updates at the same time. So you have to be careful about things like input queues in your routers. So you can increase the throughput if you basically reduce the overhead that you have in your TCP sessions. For some reason, the MSS that is used by default in TCP is 436 bytes. But we all know that most of the MTUs and most of our networks today are not even close to 536 bytes. But we see things like 1500 or 4K MTUs. So by using the defaults, we're adding a lot of overhead to the packets that we transmit. So you can get rid of that overhead if you do something very simple like MTU path discovery, path MTU discovery. So that you know what is the MTU on the path, and then you can send bigger packets, which means more information, less overhead, more throughput. Yes?
Not understanding synchronization. Let's say I'm a border router. Let's do an update, and I'm going to send a flood update to my peer group. So I walk the HTTP table and I send the update. HTTP is eventually going to get to everybody. So unless a new update comes, every router will catch up, wouldn't it? With this new update. So where would I lose synchronization?
So the cases where you lose synchronization are not the cases where you're sending, one update or a few updates that may fit in one TCP packet, for example. But the cases where you might lose synchronization are the cases where you're sending a large amount of routes. Like if you're sending the whole table to all your neighbors.
So lose a session, for instance?
Well, okay, you can lose a session, or if you're sending the whole table doesn't fit in one TCP packet. So you have to send a lot of packets. So because some of your routers may be slower or whatever, then they may be slower in acting the TCP packet. So that's where you fall out of sync. But usually it's in the cases where you have significant information to send, not when you have little information to send.
Is there a time frame when you will eventually converge? Because you will eventually converge, right?
Yes. You're right, Shane.
Is there no time frame that you should be aware of?
So no, it depends on your requirements. And what we do is we in the testing and stuff that we do, we assume a worst case. And the worst case is usually when you reboot. And you have to negotiate all your peers, you have to learn all the routes from them, and you have to propagate routes to them, right? So we assume that's the worst case. And kind of the time that we use, and we use this based on feedback from customers, is around 10 minutes. So we assume if you had to reboot your network right now, how fast can you get back to complete convergence in BGP? And of course, this is on a router-for-router basis. But it all depends on what you want, right? So we use 10 minutes, but the goal is obviously to make it a lot faster than that. So the other thing that you can run into problems that may cause loss of synchronization are cases where you send your updates, and what you receive are, of course, just the ACKs, TCP ACKs from your neighbors. And if you get a rush of ACKs on, say, the same interface, or even not on the same interface, you may run out of process level input queues, meaning you may not have enough buffers allocated for that, so you might drop the ACKs. Now, in TCP, it doesn't matter, because TCP will just retransmit the ACK, right? But what that will do is, of course, it will delay the transfer of the information. It will cause the peers to fall out of sync. So you can avoid from losing that information, then that's a lot better. So the way you do that is you just increase the size of the queue. No, not the SPD queue, the input hold queue on the interface. If anyone is interested, talk to Daniel, who's sitting over there. He developed a little formula with the rest of the team on how to do this, depending on the number of neighbors that you have, depending on the number of routes, etc., so that you don't just build your queue very big or too small.
Is there a white paper on it?
Is there a white paper on it? Do you work for Cisco? No. Sorry. So this is as close as you're going to get to the white paper for now. This is some results that we got from a lab. This is 7200 P400 on 1208TS, just because that's the latest we tested. And there's a number of routes, a number of peers. And what we're doing is we're using that 10-minute convergence time. So basically, we're rebooting the router with these many neighbors, right? And then we're using peer groups to receive the routes from someone and propagate the routes to everyone else, right? To these number of neighbors. So this is, of course, not the maximum supported. This is the maximum that we can actually converge with in 10 minutes. If you want to wait longer, yes, you can support more neighbors. So for things like 100,000 routes, let's say here, 100 peers, if we use no peer groups. Right? If we use peer groups, it grows maybe by, 20 or 30%, whatever that is. And we have these other lines here that add, for example, peer groups plus the MTU discovery to take away some of the overhead, or peer groups plus a big input hold queue to get rid of loss of information. And of course, the one at the top is peer groups plus both MTU discovery and playing with the input queue. And you can see, the difference between this line, which is the initial line, right, no peer groups, and this line up here, where from maybe 100 we go up to 450 or something along those lines. So that's what, 350% or something along those lines of improvement just by tweaking a couple of parameters. It of course means that if you have the same number of neighbors, right, the fact that you can put 450 routers and still convert in 10 minutes doesn't mean that you have to. But what it also means is that if you stay with your 100 routers that you had at the beginning, now you can converge a lot faster.
How many peers or peer group are you using? All peers are in peer group.
All the peers are in the same peer group.
That's a bogus metric.
So the comment was, that's a bogus metric. The answer is, it depends. It depends on what you're looking at. If all of these are your IBGP neighbors, no, it's not bogus. If all of these are your external clients, customers, no, it's not bogus. Yes, there are many other cases where it might be, but not for this test. Thank you for the comment. I assume you don't want to see the white paper either, right? In any case, yeah, all is fair here. Okay, so just to give you an idea of the benefits, right? Not to tell you, go do this and put everyone in the same peer group.
Do you have that in number of seconds of actual, like if it's significantly faster, or number of seconds of actual conversion?
Yes, not here, but we can talk later. So, as we showed, configuration grouping is one of the advantages here, but that's probably the least of the advantages. We're going to save on the size of our configuration. But the other one, which is the more important one, is update generation and replication. Again, you only walk through it once, and then you replicate for everyone else. Reflectors, this is RC2796. This is a well-known deployed alternative to a full mesh. It's been deployed by everyone. Not everyone, a lot of people. And what this does is it basically breaks the rules of the original BGP spec, and it allows a router, that we call a route reflector, to advertise updates that it received from an internal neighbor to other internal neighbors. So it advertises routes between what we call clients and non-clients. So routes that you get from a client, you send to other clients. Routes that you get to non-clients, and routes that you get from non-clients, you send to clients. So that's why it's called a reflector, because you get the route, you basically, the same way that you got it, you send it to everyone else. There are a couple of extra things that we add, something, not really that route reflectors add. One is called the original ID, the other one is cluster list, and these are both used for loop detection inside your network. So remember that at the beginning, we said that the reason you needed to have a whole mesh was because there was no way to detect the loop in IBGP. There's still no way. That's why route reflectors need to add these things in there so that now it can detect a loop. So in case you're not familiar with reflectors are the guys who actually reflect the routes, of course. Clients are the peers between which the routes are reflected. So a route from a client is reflected to other clients. The reflector of clients are called a cluster. You can have clients peering to different clusters, like this one, for example, is peering to this guy and to that other guy over there, and they're in different clusters. What else? And there's like non-clients, which is just regular IBGP peers. So for all practical purposes, from his point of view, there's only one other IBGP neighbor in the network, and you get all the routes from them. So as I said, only the best path is propagated. It depends on where you got it from. Where you got that best path from, you propagate it to different people. EBGP routes you send to everyone, normal BGP, right? routes from clients, you send to other clients and non-clients, because you want to, again, give the impression that everyone is connected. And if you get the routes from regular IBGP peers, you just reflect those to clients. The attributes that we saw before, originator ID and cluster lists, they're added by the reflector when the router is reflected. Only when the router is reflected. So you can have redundancy, which is kind of the theme of all this. Redundancy and hierarchy and summarization. Redundancy is a good thing. You can have redundancy. So you can have a router reflector peer with more than one reflector. A router reflector client peer with more than one reflector, even in different clusters. So to have redundancy, you don't necessarily need the reflectors to be in the same cluster. In fact, the only reason that I know of why you want to have more than one reflector in the same cluster is for administrative reasons. Because it's nice to know that those two routers over there are cluster number 5. There's really no technical reason to have two routers in the same cluster. There might be problems if you have a client peering to two reflectors and they're in the same cluster, and in a failure mode, you lose one of your sessions with one of the reflectors. You might end up not receiving all the paths, creating black holes, loops, whatever. Of course, most of the cases, this is only in a failure scenario. So in this case, what we're trying to show is we have two routers in the same cluster, and we have a route there that comes in on D. D is a client, B is a client of the two reflectors, and we have the reflectors fully meshed with the clients, which is how you have to do it if the reflectors are in the same cluster. So there was a failure of some sort. So the way the packet flows here is, of course, you get it here, D gets it, D propagates it to both reflectors, the reflector reflected to the client and to each other. So because they're in the same cluster, when C gets the route from A, C will ignore the route because it's a cluster loop. They're in the same cluster. So there was, for any reason, a failure in the link, let's say between C and D. If there was a failure in this session, then, of course, D couldn't send the update to C. It would only send it to A, and A would send it to C, but C would find its cluster ID in the cluster list, so it would ignore the route. Yes, there are ways around that, like peering with the loopbacks, for example, so that you don't lose the session. However, let's say that the link between A and B fails, right? And well, let's say you have a double failure. The link between A and B fails, and the session between C and D fails. So the packet comes in here, A gets it, A sends it to the client, right, through the loopback connection BGP session. It sends it over there, but he rejects it because it's a cluster loop. So what we would have at that point is B would know how to get there, or thinks he knows how to get there, but the physical connectivity is only through router C, and C, of course, doesn't have any routes because they were all reflected from A and they were all there. So, yes, those are failure scenarios, and if you were careful in designing your network and have proper redundancy at all levels, etc., you might not run into this. But you still might. And you might lose some of the redundancy you were actually trying to build. So, of course, the alternative is to just have your reflectors in different clusters so you don't run into those problems. Yes, the caveat with this is that because now you have two different clusters, then your clients might get more information than they did before. So there's a little extra memory utilization there. But we can guarantee that everyone can get everywhere else if you do this. So there might be, this of course, the case where there's too much redundancy. Usually, you see a client peer to 2 reflectors. In most cases, you don't see more than that. But if you were to add more reflectors just for extra redundancy, you would have a case where a client actually gets a different view from each of the reflectors. So the more reflectors you peer your clients with, the more routing information you're going to get. So depending on the capacity of your client, that may not be a good thing. Not only because it's going to use more memory, but because the added benefit of the extra views doesn't necessarily justify the extra memory that you're using on that route. You can, of course, build hierarchy in a route reflector network. And what this means is you have reflectors that have clients that at the same time are reflectors for other clients. So you have several tiers or levels of reflectors. Usually the high-level reflectors, the reflector at the top, are the ones that are fully meshed, like a normal IBGP core. And everyone else just peers with the proper reflectors. This guy is a client of these 2, and it has 3 clients, for example. This also provides, a configuration like this one provides a natural method to filter, not filter, but to limit the amount of information that you propagate downwards. So for example, let's say this guy here, and these 2 reflectors here, let's assume that we have external connectivity out there. So these guys here would each receive 3 paths from the border routers, 1 from each one. So they have 3 paths each. Now they choose the best path and they propagate 1 to the client. So the client, instead of having 3, now has only 2. Now this client is going to reflect only the best path to its clients. So at the end, the guys down here are going to end up with only 1 option instead of 3 that were at the top. So it allows to limit the information. That also means that, of course, the routers at the bottom, which may be your access routers, going to have less memory requirements because you don't have that much information. With the routers at the top, which are going to be your core routers, you're going to need more memory and maybe more speed or whatever, because the table is going to be bigger. You have more information. So behind all this, the most important thing you have to remember about route reflectors is that you need to follow the physical topology. You always want to define where your reflectors are based on the physical topology. And the best way to guarantee that there's not going to be any loops or any weird routing anywhere is by only having clients to a reflector that are directly connected to it. Remember that you get the information from your reflector. So you have to forward a packet to that destination. The way you can guarantee that that packet is not going to loop or be sent back to you or somewhere else is if you send it to the router that gave you the information. Because you know that it was the best path, so it has to send it down the same path that you chose.
That applies to your regional route reflector strategy. You need regional phone lines to compensate for you're saying you want to be directly connected to your route reflectors.
Yes. So you want to be directly connected to your route reflectors to avoid some hop in the middle that might have not made the same decision you did. Now, in most cases, to be fair, in most cases, that hop in the middle might only result in some alternate exit. In most cases, it never results in a loop. But yes, you want to, as much as you can, maintain connectivity with your reflector. Anyways, so the way you deploy your route reflectors is you divide the network into clusters. Each cluster is going to have, of course, at least 1 reflector. In a second. And you want to define where the reflectors are based, again, on the physical topology. As we saw in the last slide, on this one, the guys at the top are the ones that need to be fully meshed. The ones in the lower levels, for example, these 4 guys here are reflectors, I call it in level 2. They don't need to be fully meshed between themselves. They can only peer with the reflectors. Only the top layer are the ones that need to be fully meshed. And you still use a single IGP because things like the next hop remain unchanged. So even though you're reducing the full mesh, everything else remains the same. You still have to know how to reach everything.
Yeah, you're saying this is a very good thing, and it's true. I mean, it's more efficient, but there's also information loss, right? So depending on how you utilize your networking clusters, it means that you're limited by the top level decisions of BGP process, which means that if you appear in multiple locales and you want to spread the traffic across them, you don't want to do that, which is a little faster.
Correct. So the comment is that, this is very nice because you naturally funnel the information down the hierarchy, so the guys at the bottom get less information. But of course what that means is you're hiding information. Right? So the guys at the bottom don't know what all the guys at the top do know. So there might be cases where you might not be able to, let's call it engineer your traffic properly because the guys don't know everything. There's other cases that are well known where you can actually get into a permanent oscillation of updates with no end in sight because of a hierarchy of reflectors and the combination with other things like MED, for example. But yes, that's a very good point that you have to understand if you're going to do this. Yes?
What about configuration of the UDP? You're going to use more naturally hierarchical length.
So if you give me 2 slides, I'll get there. So in any case, the summary for reflectors is follow the physical topology. If you don't, you may not get the results you want. Again, most of the abnormalities, let's call them, are a result of failures, and a lot of them result not in a loop, but in an alternate path being used. So it may not be that bad, but just so you keep that in mind. It's better to be safe than sorry later. Yes?
You expect your core the IPGP mesh. You want to follow the for all the 4 orders to be fully meshed.
No, and that's a good comment, and that's probably the exception. So what I said before is the routers at the top level, the reflectors at the top level are usually fully meshed between them, right? They're the top level IBGP, so they're all fully meshed. Do we need to follow the physical topology there and have a full mesh up there? And the answer is no. That's where you have the normal IBGP. So as normal IBGP goes, all you need are logical connections. But that's a really good question. Everything else, when we say follow the physical topology, it means from reflector to client, reflector, etc. All those connections should be. You want to plan redundancy per client, so now you don't have to plan redundancy per cluster. You can plan it per client. So this makes reflectors very easy to grow, and if you have one router, just put it somewhere and add a link, and that's it. You're connected to a reflector. Yeah.
If you can go back to that slide, what if you don't have the lower level routers or the regional routers? What if you don't have redundancy into the higher level routers? How do you deal with reflector redundancy?
You mean like, for example, in this case, he doesn't have 2 links up? Or in his case, he doesn't have 2 links up?
There's just 1 link up.
So see, there are two levels here. One is, I guess, a logical control plane level, right? Which is where you learn the information from. And even if you have 1 link, you can still have 2 reflectors, right? That doesn't preclude you from having that. But then you have the other part, which is actually the forwarding redundancy. Of paths to the next hop, of maybe load sharing, etc. So if you don't have the extra link, don't use an extra reflector. Because in any case, physically you depend on this one. So if this extra link doesn't exist, you probably shouldn't have the extra reflector. Because if this reflector fails, you can't get there anyways. So that's the other very important part, that you always forward the traffic through the physical topology of your network. So if your topology is not such that you can actually build a hierarchy, well then you need to build it that way. So let's get to configurations. This is another way that people use to reduce the size of the full mesh. This is described in RFC 3065. And all it is you have an autonomous system and you split it into smaller autonomous systems. And they're called sub-ASICs. From the outside, it still looks like one autonomous system. So all you're doing is dividing the network internally. You preserve across your confederation, which is still your local internal network, you preserve the next hop, you preserve the local path, and the med. So that usually means is that you want to have a consistent IGP across, so you always have reachability to the next hop. Because the next hop is preserved across sub-AS boundaries. There's AS configuration sequences and sets that are used or may be used to prevent loops. So remember, right, we don't do loop detection in full mesh, so we need some way to do it. So this is how we do it. Before you ask, no, we don't support AS configuration sets. We don't support sequences. I don't know if anyone else supports sets. Never seen anyone who has a reason to use sets, but
I wasn't going there really.
Okay.
The RFC doesn't specify proper loop detection. There was an incident about 3 months ago where like every router from a particular vendor blew up because you guys and a few other people don't do loop detection because you only check the beginning because you're supposed to pre-scan AS confed sequence, and then you don't check the end. So if it hits the end, then it's still unknown AS packetry, which generates notification messages, etc. So that's something to kick that. That's the only thing we can break what happens.
we can talk about later, but no, I think what happened was that, I think what happened was not that, but the fact that the configuration RFC is not
totally
clear as to the fact that you shouldn't send, or what you should do if you get a configuration sequence from an external neighbor. And we let it through, and some other people didn't like that. So it wasn't because of a loop detection, it was because of...
It was also because you don't check the entire sequence.
So we can, talk about that later. Doesn't matter. So this is how the AS confed sequence should work all the time, which is not how it's working, and that's why we're seeing those problems. Which is you get the advertisement from someone internally with an AS path, and you propagate it internally, and you add the AS confed sequence to it, right? And when you get to the border, you just send it out without the AS confed sequence. That's the theory, of course, and with the configuration AS pre-pended at the beginning. Very simple. So if you wanted to migrate two configurations, there's really no graceful way to do that. And the reason for that is because you're breaking down your network into different autonomous systems than the original one you had. So that means that you need to change your configuration at least to now send your open message from a different autonomous system. Now your neighbors are going to be in different autonomous systems than you were before. Now you need to know that some of your seemingly external neighbors are really inside your configuration. So that you keep your next hop, you keep local private, you keep the med, etc. So there's really no graceful way to do that. That's why I found that some people don't like to use configurations because it's hard to migrate back and forth.
Well, I'm going to disagree with that point because in Cisco universe, the router BGP identifier can be the same as the confed identifier, but you can go from a full mesh with confederation simply by adding that full confederation with the same AS as the original router BGP AS, referring to no tear down and reset up of all of your peers pretty normally.
Kind of. The comment is that in Cisco BGP, you can, the way you configure configurations is you have your autonomous system number, you have a configuration ID, which is the real number, and then you have configuration peers. So the comment is that you can configure your local autonomous system number and the the confed identifier to be the same. So that allows you to basically become a sub-AS without resetting your peers, and that is correct. What it doesn't allow you to do is if you now have other sub-ASs, right? If you have a full mesh network, and now you want one part of it to be this sub-AS, then you're right, those neighbors stay the same. But if the other part of the original AS now is a different sub-AS, you have to reset those. So this is equivalent, in some maybe twisted way, to what we did originally with ISIS and OSPF. If you're going to do ISIS, start with level 2, right? If you're going to do configuration, start with the configuration ID being the same as your local AS, and then go from there. So if you wanted to now say, well, I have my AS, I want to add other networks, you can just turn yours into a sub-AS, and then just add new networks, which is actually something that quite a few people do when acquiring networks, for example, acquiring companies. So you have your own autonomous system, and you acquire someone else, and they have their own network already. You can just set BGP. Now, if you want to look externally as one hop, you can just change yourself to a sub-AS and change them to a sub-AS, and then just be one autonomous system. That's actually quite a few people do that, because of one of the characteristics that is very important with configurations, which is independent sub-AS administration. Because these are really autonomous systems. So each autonomous system can have its own policy, its own filtering, whatever you want. Each of them can have the same thing. The only caveat is, of course, you keep the local path, the net, and the next hop. But you can actually reset all those by adding the proper policies and borders. So you actually end up with independent autonomous systems inside your network. So we're going to stop for a minute.
For a hierarchy in the AS and sub-AS system when you migrate, so your new sub-AS is the same as your autonomous system. It becomes a backbone AS that all the ranges attached to it.
You could. So that's an easy way to start migrating. If you have your core AS and then add ASs to it. But once you added the first AS to the core one, because these are autonomous system, you can just keep adding and put them all in a straight line or whatever you want. So that might be a good first step. Because in any case, if you're going back to the example, if you're acquiring some networks, you are the acquiring partner, right? So you are going to tie everyone to you, for example. But no, you don't have to follow a hierarchy in that case. Not at all. So the nice thing about the independent sub-AS administration and the fact that you can actually reset everything at the sub-AS borders is what gives you that ability, right? To just integrate networks into your own network. And it also means that you can actually use separate IGPs for sub-AS if you reset the next hop at the borders. Because the whole thing with the original, what I said originally about configurations is the next hop is kept across sub-AS boundaries. So if you did that, it means you need to either have one IGP across the whole network, or you need to redistribute across at the borders. And you probably don't want to do that. So the next best thing is to just reset at the border, if you're going to do that, and just have separate contained IGPs. That way you have exactly an autonomous system inside your sub-AS, your network. Yes.
So would you run if you're doing OSPF, would you run areas on that sub-AS, or would you buy a separate IGP?
So how do you actually do this, if I mean a separate IGP? So what I mean is, so the question is, would you use areas in OSPF and say have area 0, 1, 2, 3, whatever? What I mean by a separate IGP is just a completely different process. So you might run OSPF in both sub-ASs, but they're completely independent. It's like if you were peering with me in different autonomous systems, and Cisco if Cisco ran OSPF internally and you ran OSPF internally, we just communicate through BGP, and we don't know.
So we're completely relying on a BGP to maintain connectivity within our...
Correct, just like any other inter-AS connection.
Is that a good idea?
A lot of people do that. That doesn't mean it's a good idea or not, but a lot of people do that. And what that gives them mostly is autonomy inside that AS. Right? If that is your goal, then yes, that's a good idea. If your goal for using configurations was to just simplify the mesh, well, that may complicate things a little bit.
So is the choice of confederation better for doing that sort of thing over replicated, or what is the advantage?
Better for doing what?
That where you start separate IPs. Could you do that with a cluster in the architecture, and what would be the risk?
So, could you run a separate IGP per cluster? You probably could. I wouldn't. But It would be very hard and unnecessarily, a lot of overhead. Because it would mean you would have to have at every reflector redistribution between protocols, and that may become a mess, especially if you have multiple reflectors and multiple mutual redistribution across, and you don't want to do that. No. So in any case, configuration is going to simplify your network topology, right? Because now you have ASs everywhere. You can have a hierarchy inside your sub-AS. So what that means is if each sub-AS is independent of each other, or even if not, you can have reflectors inside if you really wanted to. One of the caveats with configurations is the fact that now once you divided the network into ASs, there's no guarantee that all the ASs are going to be small. And you may have a huge autonomous system, and you might still have limitations or concerns about the full mesh. So you might want to do reflectors inside if you really want to. Good things, policy can be defined for sub-AS. And as I said, migration back and forth is not necessarily as straightforward as with reflectors. So I have this little table that kind of compares them. A lot of things are the same. Scalability, reflectors, I said very high. Medium, the only reason I said medium for configurations is because of the fact that you might still end up with a big sub-AS. But otherwise, if you divided your network correctly, probably doesn't matter. And then the migration complexity. It may be, depending on how you do it, if you can get away with just converting your whole network into sub-AS and adding as you go later, maybe a lower complexity. But if you have to change your one AS into 10 sub-ASs, that may be a lot more complicated. Not only complicated, but means downtime and et cetera. Where with reflectors, you can pretty much get away with migrating from a full mesh to hierarchical reflectors without any downtime, if you're careful enough.
Are there any, you seem to conclude that there are no, that reflectors has all the advantages of these federations. Are there any situations where you think federations have some advantages?
Advantages of confederations, individual administration of each sub-AS.
Is it not more natural in some sense in that regard?
Yeah, correct. Correct. It's basically a sub-AS. Individual administration, acquisitions is great, right? You just add it and that's it. You have a new piece of your network. So if you don't mind having maybe someone else administer that piece of your network, you're fine. So yes, both have advantages and disadvantages. You can't necessarily have independent administration for a cluster. I mean, you could, but it's not something you probably want to do.
Well, just to add to that, consideration, going back to your design that you had, the yellow design, or the backbone or all fully meshed. This would be a good idea where you have a hybrid where each region is a reflector with the backbone, because that's the most expensive link you have, where you have instead of having a fully meshed, the backbone is intrastate, depending on how you have. That would probably be great.
Yeah, correct. And the way you build a configuration, meaning the way you break up your network into pieces, depends a lot on how your network is set up. A lot may be by geography, depending on your network, maybe by department, by function, whatever. So yes, there are many ways to do this. So let's go into detection and propagation of changes. The first thing I want to talk about is a minimum route advertisement interval. So this is what the ERC says. Just so you know, we don't necessarily do it this way, but this is what the ERC says. It says that this interval is the minimum amount of time that has to pass between advertising a route to a destination to a neighbor. So it means that if the route is flapping, for example, I should wait the interval before I send it again to a specific neighbor. So the kind of reason for this is to try and do some damping, for example. Try and not propagate changes too fast. The same things we were talking about before. However, the minimum advertisement interval is a very high number. For external neighbors is 30 seconds. So you may end up waiting a long time to do this. There have been some people at Merit University of Michigan that have done some studies on how the advertisement interval behaves and the effect that it has. And they found that they found some of these things. That the advertisement interval, for example, 30 seconds as the default, may be too long. It causes unnecessary delay in conversions. Other things that they found is timers per peer may not be such a good idea as per prefix. Just to clarify, we do it per peer. And they also suggested transmit-side loop detection. And what this is if I'm sending an update to a neighbor, to an external neighbor, and their autonomous system is already in the AS path, well, they're going to ignore the route, right? Because it's a loop. Now, the problem is that if I send them an update, that means that I have to reset the timer. So I'm wasting time by sending them updates that I know or that I should have known that they're going to deny anyways. So if you do transmit-side loop detection, you don't send them anything, and you don't reset the timer, so you have to wait an extra 30 seconds before you transmit again. So in any case, so that's some of the things that they came up with. So we did our own test, just to make sure. No, not to make sure, just to know how routers did. And we built kind of the same thing or something similar to what they did, which is like 4 ASs and they're meshed. And so we're withdrawing and advertising a route from one of the ASs across the others. Yes, this is not 100,000 routes, but we can extrapolate from here. And so this is what we got. So we did 10 tests, varied between updates and withdrawals. This is the timer for the minimum route advertisement interval. The default, all of them were external neighbors, right? So the default was 30 seconds, and we said, well, why the heck do we need this timer? So we set it to 0.
I have a quick query here.
Yes.
1771 or 13 or whatever you're referencing specifies that withdrawals will not be affected by the route advertisement. So,
Yeah, I believe it says that, correct.
are you implying that, I didn't know that that's the case. Are you implying that this system implementation will be affected by the route advertisement?
That's a very good question.
I thought there wasn't.
Yeah, so the question is, or the comment is, we think the spec says that the withdrawals shouldn't be affected by the timer, by the advertisement timer interval. Because after all, you can't get there anymore, so you should just tell someone. Is this implementation affected by that? The answer is in some cases. Keep it at that. We can talk about that later. So in any case, what this does is it has timer, it has some loop detection, whether we had it enabled down here or not. And this is the total number of messages that we sent. This is the number of updates that were denied by our neighbor, meaning things that we sent that we never really needed to send because they were going to be denied anyways. And this is the conversions that we got. Okay, this is one route, I know. But you can extrapolate the number of messages. So for example, in this test, where we send a withdrawal, with the timer set to 30 seconds, we sent a total of 25 messages. Now remember we had 4 ASs, right? So between the 4 we sent a total of 25 messages, and 8 of them were denied anyways. And we converted in a minute. Right, so it took us a minute to withdraw a route between those 4 ASs. Because of the combination between the timer and the fact that we send things where we probably shouldn't have sent them. Or the fact that we didn't detect the transfer loop. We did some other things, for example, same setup but with a very low timer, and what we found is it's very fast conversions, but it's even worse, right? Because we now send more messages, and we get more updates tonight. So, if you think, well, if we just take the timer down, but we don't, and that's all we do, we're going to be generating more messages and more denied updates. So if you extrapolate from one route to 100,000 routes, that may not be the best thing to do, right? Because you're going to be sending a lot more information.
Why is the update increased, the denied update increased in the time?
Part of the reason is because now we're sending the updates faster. So see, if you wait, what that means is that you might actually get an update and then you get a withdraw in those 30 seconds. So, they kind of cancel themselves out. But if you do it faster, then you might not get it fast enough. Right, so that's why maybe the number of messages increases and the number of denies increases. So then we added loop detection. And we did some of the same tests. And you can see, of course, that the number of updates denied is 0. Because if we're doing the transfer loop detection, then we don't need that. Or then we're never going to get into that situation. One of the important things is, for example, in test 6 here, which was the same as the original one up there, except that with the transfer loop detection, we basically cut the conversion in half. Right? And of course, the other good thing is the total number of messages was cut to half, even with the same timer. Right? And then with zero, what we also found was that, again, the number of messages increased. So what we decided to do was play with 1 second and give it a little bit of time to settle. And we came with what we thought for one route was probably the optimal timer.
Did you try 7?
No, I've heard 7.
7 was done in a couple papers by models.
Yeah, so I've heard 7 somewhere. We haven't done it. And one of the things we plan to do is, of course, do this with more routes. At least, one.
How many routes did you use?
For this is 1.
Just one route?
Correct. Right, so all we wanted to see was the general effect. But, you can almost extrapolate some of the things here. But yes, I've heard 7 some places. We're working on some other tests to try and figure out.
And so, number 2, you only have 1 route, and you give these 25 messages to get it across?
Correct. Now, this is 25 messages between the 4 ASs. So not only from one route, right, but between the 4 ASs.
Even in the worst case, it's 24 messages. You assume that each one announces it by 3, which wouldn't actually happen. Right? So you have an update and just an update and update the neighboring AS and say that the result is 24.
In the worst case, 43.
There's 6 physical links.
1, 2, 3, 4, 5, 6, yeah.
So how do you get 25? How do you get 43 update messages?
Well, no, what happens is that some of the messages are not necessarily only updates and withdrawals, but what happens is you don't necessarily have one path to start with. So when the path gets withdrawn, even if it was from the origin, and the other paths came from the same origin, you don't necessarily assume that those links fail, even though the path may be the same, right? So the path was 1 to 3 in the original route, and the withdrawal came from the link between 2 and 3. And the other alternatives were 4, 1 to 3, or 5, 1 to 3, longer AS path, even though the end connection was the one that was lost, you don't necessarily realize that. Right? So what happens a lot of times is you end up selecting the second best path, not necessarily waiting for the other guy to announce to you what the best path should have been. Right? So you end up having more routes. It's kind of an effect of maybe counting to infinity, yeah? Where you keep recursing through your routes. Now that is, and I want to make this very clear, that is not because of how we implement this. That is because that's how the protocol works. Yes.
What does the timer cost regard instantly in the network?
So the question is, will the timer cause a lot of instability? Well, that's why we here went back from 0 over to 1. And the reason is, if you're very aggressive, you might be generating more messages than you actually need to. Sue was mentioning a timer of 7. And I've heard this in some other places that, of course, this is with one route. Now, if you have more routes that are changing, for sure, the timer that you need to use is a little bigger, so that you compensate more for the fact that you have more updates, right? Now, the other thing about this is that, the routes that are changing in your network that you see propagating through this inside your network are really external routes, right? Because any internal flap that you have, you should see it in your IGP, not in BGP. So if the external routes are flapping, you should probably stop that. So you should do dampening at the border. So, I think where I'm trying to go is the solution is not just changing this timer. But the solution is coupled with the fact that if you have dampening at the borders, if you manage to distribute the information faster, but you can dampen the flapping at the borders, then a lot of the potential instability that it might cause inside your network is reduced. So this is just to grasp you what we saw before. Yeah.
At what point do you apply the loop detection? Is that just before you're sending the update to the peer? Or is it during computing the update?
Well, the way we did it, because of course BGP by default doesn't have transfer side loop detection, the way we did it, we just applied a filter with an AS path access list. So the way we do it in our implementation is when you build the update, you find out that you don't have to send it, so you stop there. Not right when you're going to send it. So
then do you at times actually have to send a withdrawal?
Do you at times have to send a withdrawal? No.
So, classic example would be, you have it out, and you send to your peer, it passes the TX loop detection. And then you have another route now. The old route is gone, but the new route that you compute doesn't pass the update check, the TX loop detect check.
Meaning you don't send it? Meaning you shouldn't send it?
Yeah. In that case, you need to actually send a withdrawal to your peer.
No, you should have sent the withdrawal for the original route.
But you can always send an update. That's why you send withdrawal.
Oh, I see what you mean. Yeah. So that's something that, yeah.
Wouldn't the route map process mess up?
Yeah, so the route, in this case, the route map process, oh, yeah, correct. Yeah. So in any case, going back, okay, what we did was putting a filter. Yes, that doesn't work in all the cases. You're right.
Okay.
So the way this would have to be implemented internally is you have to check it the other way. Yeah, go ahead.
But what it's done is, attempt to send an update, and by some reason, policy or whatever, the update is not supposed to be sent, you generate a withdrawal.
So then you generate bogus withdrawals.
Bogus withdrawals. You do check, you do need to have a withdrawal on the
You don't know that. You don't know whether you can send the update in the first place.
You do.
So I guess we need to go read the code a little bit more. Yeah. I couldn't hear you. Correct. So, okay, so the way we did it for the test, which is adding a different filter for every external peer, that wouldn't work with peer groups, right? Because you can have all the neighbors in the same peer group. If this was implemented internally some other way, then yes, it should work. So this is not implemented. Right? This is something that was suggested by that paper, but something that has to be investigated a lot more. Because you're right, there are other issues in there. Yes.
In here for the suggested changing the 30 seconds back, so we down forward to 60.
Yes, please do. Next up, reachability. So we all know that we need to be able to reach the next hop for the route to be valid. If the next hop is not reachable, then the route is invalid. And that's very, very, very simple. The reachability has been provided by the IGP. And of course that is because BGP is going to depend on the underlying IGP to reach all the next hops. Any changes in the network, part of the speed at which we're going to detect them is going to depend on the IGP itself. Right? If the next hop is not reachable anymore, we need the IGP to notify us. If the characteristics of the reachability change, like the metric, for example, remember that one of the selection criteria in the selection process is IGP cost. So if the cost changes, we might actually have a different best path. So all that depends, of course, on the IGP to forward that information. There are other timers that are going to, and this depends a lot on implementations, they're going to check or not periodically to see if the next hops changed or not. So there may be an extra consideration that you need to have depending on what implementation you're using.
Based on 5 layers?
not true that we don't have an equivalence classes with different next stops, and as soon as we are notified by IGP, we can trigger the calculation.
So it depends, as I said, it depends on the implementation. Our implementation, we have a scanner process that we go and check periodically. We should go to the next hop. So there are some cases where we might not know that the next hop changed until the next scan. So, yeah, there's a timer. It's called scan time. Yes. As with all the knobs, you know, treat with care, and it's your responsibility for whatever is happening. It's my official disclaimer, and I'm on tape, so.
What was the default time?
The default is a minute. Yes. Correct.
One more question. Is there a way to measure how long it takes to scan the table?
Is there a wish?
You mentioned about two.
Yeah, so the question is there a way to measure how long it takes to scan the whole table? No. No, so we don't have a way to know that. In any case, you need next hop reachability, so you have to make sure the IGP has that in its tables. So there are usually three ways or common methods that are used to guarantee this. One is enable the IGP on the external interface. Of course, you use passive interface, you don't end up here with OSPF with your external neighbor. This, of course, has a caveat that if your external links are unstable, then your IGP is going to be unstable. The IGPs, because are a lot less resilient to change than BGP. You can have a little more leeway in there. You can use things like really should be connected and add the information to the IGPs. One of the caveats there is that now the information becomes external. So in the case of OSPF, you have external LSAs that you need to transfer it everywhere in the network. You can use something like next hop self to basically change the next hop so that your next hop is not your external peer, but now it's the local IBGP border router. That has the advantage that your IGP should already have the route in it. Maybe the disadvantage is that you don't have an accurate metric of how to get to the real next hop. So we had two different next hops to the different peers, and the only difference between the two was that the metric to get there, if you changed to next hop south, then you would lose that granularity. So it depends on how you want to treat your IGP.
But that was your only exit out.
Yeah, but if that was your only exit out, then who cares? Correct. Dampening, RC2439. So what a route flap is defined in there is as a change in a route or a change in characteristics of a route. So we all know what dampening is. What dampening is the route is flapping up and down. So what we do is we penalize the route because we don't like flaps. So there's a point in time when we suppress the route because the penalty reached a certain number or past a certain number. So this means this is also true when there are changes in the characteristics. So you start getting updates that now there's a different MAD or a different whatever other attribute in there. That is considered a flap. So the way dampening works is this time and this penalty, you start flapping and you start assessing penalties. There is a limit that is called the suppressed limit. Now the route is not, what the suppressed limit is once you, above there, you should suppress the route, meaning you shouldn't advertise the route anymore, even if it gets propagated and propagated. You are not going to suppress the route at this flap, but you have to suppress the route when, after the penalty is already above the suppress limit and the route flaps again. So you don't suppress it from when it flaps here, but you suppress it when it flaps here. So it means that you have to, of course the decay from here to there is exponential depending on the half-life that you configure. So you have to be careful if you're going to implement dampening to make sure that this time between let's say that maximum point and this over there is long enough so you can actually get a flapping. And so you want to make sure that, in other words, you want to make sure that your maximum penalty is not the same as your suppress limit. Because if it is, there's no way you're ever going to get anything dampened. Because the penalty is never going to be higher than the suppress limit when a flap occurs, which is what needs to happen for it to be dampened.
If you do a BGP soft reset, none of your parameters are actually changed, does that count as a route supply?
If you do a soft reconfig and nothing changed, does that count as a flap? No. So this is what I said before, the penalty must be greater than the suppress limit for it to be suppressed. And here's another little example of what I said before. If the suppress limit is 1,000 and all of a sudden something flaps and now the new penalty is 1,200, you won't suppress the route there. The penalty is going to decay, and if it flaps before it reaches 1,000, that's when you're going to suppress it. So you want to make sure that that time frame there, finding your half-life, is big enough so that you can get another flap. So you can configure things like the half-life, which is going to indicate how fast the penalty decays. The reuse limit, this is once the penalty gets down, decays to that reuse limit, then you use the route again. Suppress limit is if the penalty is higher than that limit and the route flaps, then you're going to suppress it. And the maximum suppress time, so this is how long maximum you're going to keep the route suppressed before you put it back in service. There are some things that are actually calculated. One of them is max penalty, which is that formula. So you can, knowing that you basically set everything else, you can pretty much know what the maximum penalty is going to be. In the iOS implementation, the maximum penalty has to be less than 20,000. That's because of how we set up the formula internally. So here's an example. If you set the half-life to 30, the reuse limit to 800, and the max suppress time to 60, then the max penalty will be 3,200. There's a couple of examples here that I have. This one is for a small suppress window, and this is exactly the same example as I had before. Now in this case, the suppress limit is 3,000, so the max penalty comes up to be 3,200. So what this means is that you need to have a penalty, or you need the route to flap between the time that the penalty is 3,200 to the time that the penalty decays to 3,000, which is the suppress limit. So no matter what the penalty was before, let's say it was 2,500 and you flap, then you go to the maximum. Penalty by default is 1,000. So you go to the maximum, which is 3,200, so it starts decaying. According to the half-life, which is 30 minutes, it's going to take you 3 minutes and 45 seconds to get down from 3,200 to 3,000. So it means that if the period of the flapping is longer than that, then the route won't be suppressed. Right. Of course, there's this other example, which is an example of a bad configuration, which is, in this case, the suppress limit is set to 3,000, and you run the formula, and you end up with a max penalty of 3,000. So it means that the maximum penalty that anything can have is 3,000. So there's no way that a route can have a penalty that's higher than the suppress limit when it flaps. So you would never suppress it, correct? So you can have routes, flapping all over and you would never suppress it. There's actually a document that was published by RIPE 210 that I think it was documented in some of the best practices of how people configure dampening. And some of the configurations that they had in there would actually never dampen anything. And of course, the very interesting things is that you went to look in some of the providers' networks, routers, and you would see that configuration in there. Of course, little they knew that nothing was being dampened, even if it was flapping. Recently, I think in the last meeting, they issued a new document with the numbers corrected. So that now you can actually dampen stuff if you follow those recommendations. So kind of a summary of this, you might want to, after more testing, play with the advertisement timer. Again, all this is your risk. When transmit loop detection is available, that is probably a good thing. You want to choose an appropriate way, depending on your IGP, to carry the next hops. And you definitely want to implement dampening at all your border routers. So that's all I have. Any questions? Comments? Flames? Okay, thanks.